Hello students, welcome to the course on statistical methods for psychological research. Now we are going to learn about hypothesis testing with large sample sizes. First, we will consider single sample mean test procedures for large samples. This constitutes part 1 of the lesson. We are going to learn in this session to propose a null hypothesis for the problem on hand, to decide the alternate for the problem on hand, fix the test statistic for the cases where standard deviation is known or unknown, carry out the test procedure and make a decision. First important consideration, we first need to propose a null hypothesis. Recall that a null hypothesis indicates a natural or normal or a standard or well established result, and it must be falsifiable. It is important that a null hypothesis uniquely fixes a normal distribution for the variable in the population. What is a probability distribution? Suppose a box contains 2 1 rupee coins, 5 2 rupee coins and 3 5 rupee coins. If we randomly select a coin, the probability for getting the 5 rupee coin is 3 by 10. In the same way, we can compute the probability for each coin. The following table gives the distribution of probabilities. Here we mean the list for various outcomes. The first row contains the coin denomination 1, 2, 5. The second row contains the probability values. We can visualize in another way also, because if the number of outcomes are very large, one can find its distribution and express it using mathematics or a graph. We have shown here 2 pictures. One picture has having vertical bars, another one is a smooth curve. When you are having few number of cases, you can erect vertical bars for each outcome. If you are having more and more number of outcomes, the vertical bars are condensed to a curve. Sampling distribution. The distribution of a sample statistic is called sampling distribution of that statistics. In applications, it is found that many variables and statistics is not subject, it is actually a function computed from a sample have normal distribution. The mean of a sample is shown to have a normal distribution for a sufficiently large sample. For instance, if the sample size exceeds 30. What is standard error? The standard deviation of a sampling distribution is called standard error. Mathematically, it is shown that the mean of a sample which is obtained from any distribution has normal distribution with the mean mu suffix 0 that is equal to that of population. The standard error of the sample mean is sigma divided by square root of n, where n sigma is the population standard deviation. Look at these diagrams. The top one is gives the normal curve for the population, the bottom curve gives the normal distributions for the sample means. You can see that they are in the same alignment, vertical alignment, but the dispersion that is exhibited by the spread, or we call standard deviation or variance. So, the spread along the x axis is large for population, and for the below diagram it is small, because this is a sampling distribution of mean. So, you have to understand that the sampling distribution will have a smaller spread. The sampling distribution of the mean is normal with the mean mu. One standard error equal to sigma by root n if sigma is known. I will consider the case where sigma is unknown. If the population standard deviation is unknown, the standard error of the sample mean is computed by small s divided by square root of n, where sample standard deviation s is computed with the divisor n minus 1. For instance, if you compute s square equal to 1 by n minus 1, sigma 1 to n x I minus x bar square, you can see that the sum of squares more elaborately n sum of squares is divided by n minus 1. We also have that x bar minus mu suffix 0 divided by standard error, because we have shown two standard errors with the case of sigma known and sigma unknown. That is why I put S e in the denominator. This ratio is normal with mean 0 and standard deviation 1. This result is the basis for testing of hypothesis on mean using a large sample. After stating the null hypothesis, we state the alternate hypothesis. This is a statement the analyst wanted to prove or wanted to disprove. An alternate is usually the negation of H. The purpose of having H is, in case H is rejected, the alternate hypothesis will be accepted. For example, if H is mu equal to 100, then alternate k would be, I have given three possibilities. The first one, mu is not equal to 100, the second one, mu less than 100 or mu is greater than 100. This is dictated by the problem at hand. Level of significance, fix a level of significance denoted by alpha. What do we need? Why do we need it? This is the probability of rejecting a true null hypothesis. Rejecting a true hypothesis is an error, and committing it is a risk we take. We can't avoid the risk, therefore, we have to give some small probability for that to happen. In other words, this is the risk we would like to take in committing this error. Statisticians and analysts usually take alpha equal to 0.05 or 5%. That is, we are willing to take 5% risk. Depending on the severity of the problem, we may be willing to take a risk of 10% or 1%. It is up to the analyst. Decide the test statistic. From the fact x bar following normal distribution with mean mu 0 and standard error sigma by root n, we define a ratio z equal to t of x minus mu 0 divided by sigma by root n, which is called critical ratio. This variable has a standard normal distribution. What is critical region? Now, we shall decide the critical region. This specifies a region or interval in the number line, so that when the computed z value falls within the critical region, we reject the null hypothesis. You can see this diagram, it is a representative diagram. You can see that the alternate hypothesis is written at the top, mu less than mu suffix 0. For this, the critical region is shown in red color, reject H 0 at the left end, and you can see the diagram, the shaded region that is equal to alpha, that is the area of that shaded region is alpha. You have to understand that when object falls in the red colored area, the probability is alpha. Please note that the value can be anywhere, but we are going to make a decision. If it falls on the red line, we are going to reject it, and for that we need the probability alpha as a level of risk. For the alternate hypothesis mu greater than mu 0, I have shown that critical region on the right side of the straight line. Again, above the red color line, there is a shaded region under the curve. That area will be having the value alpha. So, you can think of the alpha as the probability for the shaded region. So, whenever my critical ratio falls on the red line, I will be rejecting it. That will happen only with the probability alpha. In the case of mu is not equal to mu 0, you can have both tail. On the right side, if you get the value, you reject. Left side, you get the value, you reject. Now, how far I can go? The idea is total probability of committing error, that is rejecting H naught when it is true, it is alpha. Therefore, on left side I have put alpha by 2, right side I have put alpha by 2. So, in either way, whenever the critical ratio falls on the left side or right side, then we will be rejecting it, but the probability is only alpha. The values that decide the boundaries of the critical region are given below, and our first column level of significance is indicated. We are taking only two values, because these are the often used levels in research. Alpha equal to 0.05 or 5%, alpha equal to 0.01%. So, in the first two rows you look at it. For first row, the second column is two tail test, that gives the interval minus 1.96 to plus 1.96. This is indicating the boundaries. It is not that is a critical region. For 1%, the boundaries are defined by minus 2.58 and on right side plus 2.58. The third and fourth column gives one tail test. The first entry is 1.645 and on the other side minus 1.645. So, on right tail test, whenever a value goes beyond 1.645, we are going to reject. In the case of left tail test, whenever the value goes below minus 1.645, we are going to reject. The same way the second row can be discussed. An example, again it is what I have given the table, it is shown in the diagram. The normal curve is drawn, the midpoint is 0 and there is a shaded region that is marked as 0.05, that corresponds to minus 1.645. So, the rejection region is on left side, that is the red color region. Whenever a point falls in the red color region, we are going to reject, but that will happen with the probability of 0.05. So, the idea is whenever you reject using this technique, you may be committing 5 out of 100 cases. We have come to the end of this part 1. We will be continuing this in the next video. Thank you.